You are standing on the surface of Mercury. The sky above you is black. Not dark blue, not dark gray. Absolute black. The black of space itself. Because Mercury has almost no atmosphere to scatter light. In that black sky, the sun hangs massive and brilliant, 3 times larger than it appears from Earth, 7 times brighter. A white burning disk that takes up a significant fraction of the sky. You have been standing here for 88 Earth days. That is 1 Mercury year. 1 full orbit around the sun. In 88 Earth days, Mercury screams through its entire journey around the sun and comes back to where it started. But here is the problem. The sun is in exactly the same position in the sky as it was when you arrived. It has not moved, not 1 degree. You have lived through an entire Mercury year, a full trip around the sun, and the sun has not set once. You are not even halfway through a single Mercury day. On Mercury, a year is shorter than a morning. Let us make this precise, because the numbers are genuinely strange. A Mercury year. The time it takes Mercury to orbit the sun once is 88 Earth days. A Mercury day. The time it takes Mercury to rotate once relative to the stars. What astronomers call a sidereal day is approximately 58.6 Earth days. So far, this seems normal. 58.6 days to rotate once, 88 days to orbit once, a day shorter than a year. But here is where it breaks. What we experience as a day as humans, as hypothetical Mercury visitors, is not the sidereal day. It is the solar day. The time from one sunrise to the next sunrise. The time for the sun to return to the same position in the sky. On Earth, our sidereal day is 23 hours and 56 minutes. Our solar day is 24 hours. The 4-minute difference exists because while Earth is rotating, it is also moving along its orbit. The sun appears to shift slightly against the background stars each day, and Earth must rotate a tiny bit extra to catch up. On Mercury, this correction is enormous. Mercury rotates slowly, once every 58.6 Earth days. But it also orbits incredibly fast, completing a full year in just 88 Earth days. The planet is spinning slowly while racing around the sun at nearly 47 kilometers per second. These two motions, the slow spin and the fast orbit, nearly cancel each other out. The result? A Mercury solar day, one sunrise to the next sunrise, lasts 176 Earth days. 176 Earth days from one sunrise to the next. 2 full Mercury years fit inside a single Mercury day. If you watched a sunrise on Mercury, by the time the sun set and rose again, Mercury would have traveled twice around the sun. But here is the question that the competitor never asked. Why? Why does Mercury rotate in exactly 58.6 days, a number that produces this precise relationship with its 88-day orbital period? The answer is one of the most elegant examples of gravitational physics in the solar system. Mercury is trapped in what astronomers call a spin-orbit resonance. For every 2 orbits Mercury completes around the sun, it rotates exactly 3 times on its axis. Not approximately, not roughly, exactly. 2 orbits, 3 rotations, every single time. A perfect 3-to-2 ratio, locked in place by gravity and maintained for billions of years. This resonance is not a coincidence. It is what the sun's gravity forced Mercury into over billions of years. When Mercury first formed, it almost certainly spun at a different rate faster, probably the way most young planets spin after formation. But Mercury orbits close to the sun, very close. And the sun is enormously massive. The tidal forces from the sun, the same gravitational differential that creates Earth's ocean tides, acted on Mercury's slight asymmetry in shape, creating a slow, continuous braking force on its rotation. Over hundreds of millions of years, this tidal braking slowed Mercury's spin down and down and down. But Mercury did not slow all the way to a 1-to-1 resonance. 1 rotation per orbit, which is what our moon does, permanently facing Earth with the same side. The reason is Mercury's eccentric orbit. Mercury's orbit is not a circle. It is an ellipse, significantly elongated. When Mercury swings close to the Sun at perihelion, it moves faster. When it swings far at aphelion, it moves slower. This variation in orbital speed created a gravitational sweet spot. When Mercury's rotation rate reached the 3:2 resonance, 3 spins per 2 orbits, the gravitational torques from the Sun averaged out over each cycle, and Mercury settled into a stable configuration. It is gravitationally locked, but not the way our moon is locked. It is locked into a more complex, higher-order resonance that only exists because of Mercury's elongated orbit. The 3:2 ratio is not arbitrary. It is the specific resonance that Mercury's orbital shape made stable, and it is the direct cause of the day longer than a year paradox. Now let us talk about what this resonance produces on the surface. Because if the day longer than a year fact is strange, what happens to the Sun in Mercury's sky is genuinely impossible feeling. Stand on Mercury's surface near the equator at perihelion, the point in its orbit where Mercury is closest to the Sun and moving fastest. You watch the Sun rising in the east. It rises, it climbs, and then it stops. The Sun stops moving across the sky. It hangs completely still for a moment. Then, it begins to move backward, west. It is setting in the direction it just rose from. The sunrise is reversing. The Sun is going back below the horizon. Then, it stops again. Then, it moves east again, rises a second time in the same morning, and continues its slow climb across the sky. This is not a dream. This is not an optical illusion. This is what actually happens on Mercury near perihelion, and it is the direct result of the 3:2 resonance interacting with the planet's eccentric orbit. Here is the physics. As Mercury approaches perihelion, it speeds up dramatically in its orbit, the same way a ball on a string moves faster when pulled inward. At perihelion, Mercury is moving so fast in its orbit that the angular rate at which the Sun appears to move across its sky, driven by the orbital motion, briefly exceeds the angular rate of Mercury's own rotation. The orbital motion is outrunning the spin. For a brief window, Mercury's rapid orbital motion overwhelms its slow rotation, and the Sun appears to move backward across the sky. The orbital contribution to the apparent solar motion temporarily dominates, reversing the direction the Sun seems to travel. Then Mercury passes perihelion, slows down slightly, and the rotation takes back over. The Sun resumes its normal westward drift. The entire retrograde episode lasts approximately 8 Earth days. 8 days during which the Sun rises, reverses, and rises again. Or for observers on the other side of the planet, where sunset is occurring 8 days during which the Sun sets, reverses, and then sets again. This happens twice per Mercury solar day, once at each perihelion passage. Imagine watching that. Imagine the cognitive dissonance of a Sun that changes its mind, that rises, reconsiders, retreats, and then commits to rising again. There is nowhere else in the solar system where this happens. This is a Mercury exclusive, but let us not stay abstract. Let us actually live through a Mercury day. You arrive on the surface at dawn at the second sunrise, after the retrograde episode has played out. The Sun is massive in the black sky, 3 times larger than from Earth, 7 times brighter. Already, within minutes of sunrise, the surface temperature is climbing. There is no gentle warming, no morning cool. The heat arrives like a door opening into a furnace. Over the next several Earth weeks, because sunrise to noon on Mercury takes roughly 44 Earth days, the temperature climbs from around -180 degrees Celsius at dawn to 430 degrees Celsius at noon. A 610-degree temperature swing, from deep freeze to molten lead territory, across a single morning. There is no atmosphere to buffer this. No air mass to hold the nighttime cold or the daytime heat. Every photon of sunlight that strikes the surface is absorbed directly. Every photon lost to space at night leaves immediately. Mercury's surface responds to solar radiation with the speed of bare rock in vacuum, which is exactly what it is. At noon, you are standing on rock that is hot enough to melt zinc, hot enough to vaporize most organic compounds on contact. The sun hangs directly overhead, enormous, white, merciless, and will not move for another 44 Earth days. 44 days of noon, then begins the long afternoon. The sun begins its glacially slow descent toward the western horizon. Over another 44 Earth days, the temperature drops from 430 degrees toward minus 180 degrees. And then, near the western horizon, the retrograde episode happens again. The sun slows, stops, moves eastward again briefly, sets, rises once more. Then finally, definitively, sets. Night, 176 Earth days after the first sunrise. You have lived through one Mercury day. Mercury has orbited the sun twice. Here is the part that nobody tells you. For most of human history, we thought Mercury was tidally locked, the way our moon is locked. One face always toward the sun, permanent day on one side, permanent night on the other. This was the consensus view for decades. It seemed logical. Mercury is close to the sun. The tidal forces are enormous. Surely it would have been pulled into a simple one-to-one lock by now. Planetary science textbooks stated this as fact. They were wrong. The error persisted because Mercury is extremely difficult to observe from Earth. It is always close to the sun in the sky, visible only briefly before sunrise or after sunset, and typically when it is at a disadvantageous angle. The surface features are nearly impossible to distinguish with most Earth-based telescopes. In 1965, astronomers Gordon Pettengill and Rolf Dice used the Arecibo radio telescope to bounce radar signals off Mercury's surface. By analyzing the Doppler shift in the returned signal, the way the radar echo was spread by the rotating surface, they could measure Mercury's rotation rate precisely. The result was 58.6 days, not 88 days. Not tidally locked, something stranger. The discovery required a complete rewrite of Mercury's understood behavior. If it was not simply locked one-to-one, what was it? Italian astronomer Giuseppe Colombo, working with data from the first Mariner 10 flyby in 1974, recognized the 3-to-2 resonance and explained why it was stable. We had been wrong about the basic rotation of the innermost planet for the entire history of astronomy until 1965. One of the most fundamental facts about our nearest planetary neighbor, how fast it spins, was unknown until radar technology gave us the ability to measure it directly. The 3-to-2 resonance produces one more consequence that is rarely discussed. Because of the exact ratio, 3 rotations per 2 orbits, Mercury has 2 specific points on its equator that always face the sun at perihelion. Astronomers call them the hot poles. These are not just warm points. They are the consistently hottest places on Mercury, receiving the maximum possible solar radiation. At the moment Mercury is closest to the sun, and the sun is largest and brightest in the sky. At these 2 points, the sun is directly overhead at perihelion. Every single time, without fail. The 3-to-2 resonance guarantees it. One of these points faces the sun at every odd-numbered perihelion, and the other faces it at every even-numbered perihelion, alternating with perfect clockwork precision. The temperature at the hot poles can exceed 430 degrees Celsius. The surface rock glows. 90 degrees away from the hot poles at what astronomers call the warm poles. The sun is always near the horizon at perihelion. These regions receive far less radiation at the critical moment. They are significantly cooler than the hot poles, a difference of roughly 100 degrees Celsius between areas only a quarter of the planet's circumference apart. Mercury does not have uniform hot and cold sides. It has two specific hottest points, two secondary warm regions, and everything else distributed between them, all determined by the precise 3:2 ratio of the spin-orbit resonance. The geometry of Mercury's rotation is written into the temperature map of its surface. Step back and think about what Mercury's relationship with time actually means. We measure our lives by sunrises and sunsets. The day-one rotation of the Earth relative to the Sun is the fundamental unit of human experience. We wake, we work, we sleep. 24 hours. Once. Again. For the span of a life. On Mercury, a life measured in sunrises would be a very short life. If you lived on Mercury and marked the passage of time by sunrises the way we do on Earth, your entire human lifetime, say, 80 years on Earth, would contain only 166 Mercury sunrises. 166 mornings in 80 years. Not because time passes differently, but because each morning is 176 Earth days long. The sun rises, and by the time it sets, children have been born. Seasons have changed on Earth. Elections have occurred. Empires, in historical terms, have risen and fallen. One Mercury morning. And within that single morning, Mercury will have orbited the Sun twice. The shortest year in the solar system, contained entirely within a single day that should not exist. The 3:2 resonance that created this is not rare in the universe. Similar resonances exist among Jupiter's moons, among Kuiper belt objects, throughout the solar system, wherever gravity has had enough time to work its patient arithmetic. But nowhere else in our solar system does the combination of a short year, a slow rotation, and an eccentric orbit produce something quite this strange. A world where the sun rises, changes its mind, and rises again, where noon lasts 7 Earth weeks, where an entire year is shorter than a morning. We have sent 2 spacecraft to Mercury. Mariner 10 in 1974. Messenger from 2004 to 2015. Bepi Colombo, launched in 2018, is arriving in 2025. Each time we go, Mercury reveals something we did not know. The spin was wrong for centuries. The hot poles were not discovered until Messenger mapped the surface in detail. The retrograde sunrise was a theoretical prediction before it was confirmed by spacecraft data. Mercury keeps correcting us. A world that barely exists in our sky, hidden in the sun's glare, visible only at the edges of dawn and dusk, keeps showing us that we fundamentally misunderstood it. And the strangest thing about it is still the simplest. The sun rises, hesitates, goes back, rises again, and will not set for 176 Earth days. One morning, on a planet where that morning contains an entire year.